Today, we're going to spend our day reviewing some material that's going to help us with this prior knowledge to verifying trig identities. So some of the topics that are going to help us with this are factoring, simplifying rational expressions, adding and subtracting rational expressions, and then just reviewing trig identities, which help us evaluate. So looking at a couple of factoring problems, remember, in order to factor, first and foremost, you want to find GCFs if you have any. So in the first one, notice that between the two numbers, they have a 2 in common, as well as an x. So factoring that out, that then leaves you left over with an x minus 5. Because the x minus 5 is not factorable any further, all we could do to factor was take out the GCF, and we're done. If we look at the next one, same concept. We start by looking for a GCF. Every single one of these numbers have something in common. They all have a 4. So that's going to be a part of the GCF. There are no variables that they all have. So once I take out that 4, it leaves you with an x squared plus 7x minus 30. What I have left over in parentheses is something that I can continue to factor. What multiplies to negative 30 but adds to 7? Well, I'm going to bring down that GCF, and then we'll be able to create two binomials where, once again, what multiplies to negative 30 and adds to 7, well, that's going to be a positive 10 and a negative 3. And then once we've done that, we have factored as much as possible, and so we're done. When you're asked to simplify rational expressions, first and foremost, in order to simplify means that you want everything as factored as possible. If you look at the numerator, you have a binomial. There are no terms that they have in common, and so there's nothing that I can do to factor that x plus 5 any further. If I look at the denominator, x squared minus 25, remember this is a difference of 2 squares. I can turn this into an x plus 5 times an x minus 5. Once everything is as factored as possible, now I can start looking at what's in the numerator that's also in the denominator that I can start reducing. Both of those have a factor of an x plus 5, so I get to reduce those down. However, remember, you still have a fraction. That x minus 5 is in your denominator because there's nothing left over in the numerator. It's technically a 1. I can't simplify this any further. This is my answer. When you're adding rational expressions, anytime adding or subtracting fractions, you have to have a common denominator. Right now, that first number isn't a fraction. So think of it as over 1 if you want. We have two different denominators. We have to find a least common denominator, and so that way we can start combining the fractions. Well, if I look at 1 and x plus 6, this is a package deal here. I can't factor that any further. Those two terms are very different, so x plus 6 is going to be then that least common denominator because you essentially multiply them together. 1 times x plus 6 is just x plus 6. So that means that I'm going to have that LCD of x plus 6 in both of my new fractions. Because the numerator started off as a 2, it's now going to not just be a 2 if I had to change the denominator. Since the 1 turned into an x plus 6, that means that I had to multiply both the top and the bottom of that fraction by an x plus 6. If I look at the second fraction, the denominator hasn't changed, which means the numerator won't change. Now that they have the same denominator, I can combine the fractions by keeping it all over that LCD. And now we can go ahead and start trying to combine like terms in the numerator. So that involves us getting rid of any parentheses on top. So that turns into 2x plus 12 plus 4x minus 4, still all over that least common denominator. Combine like terms. Well, 2x and 4x turn into 6x. 12 minus 4 is going to give us a positive 8. Still all over that x plus 6. Last step is to do what we just did in the previous slide. Try to simplify down if at all possible. And in order to do that, you have to have everything as factored as possible. The numerator can factor because there's a GCF. If I take out that 2 that they have in common, it leaves you with a 3x plus 4. The denominator of x plus 6 can't be factored because there's no common factor on both the top and the bottom. I'm not able to simplify anything down any further. This would be my final answer. If we take a look at a subtraction problem, once again, we have to have a least common denominator. Notice that my first denominator is 3x plus 6. This is technically factorable. It really is the same thing as if I take out that GCF, 3 goes on the outside, and I have an x plus 2 still left over. My other denominator is a monomial. Well, binomials and monomials are very different. So once again, it's essentially a matter of multiplying those two things together. So 3 times 2x is 6x, and then we still have that binomial of x plus 2. So this would become our least common denominator. So that is what I'm going to turn both of my denominators now into. But remember, it can't just stay 5 and 3 as my numerator. What I multiplied the bottom by has to get multiplied by the top. So once again, originally my denominator is 3 times x plus 2. So what's different? Well, it's a 6x times x plus 2. We essentially multiplied the first denominator by a 2x. So that means I have to multiply the top by 2x. How did the second denominator turn into the LCD? Well, it already has the x, but the 2 turned into a 6, and there's this binomial of x plus 2. So essentially, we multiplied by 3 times x plus 2. Now that they have the same denominator, I get to put it all over that LCD, and I get to combine the numerators. Well, 5 times 2x is 10x, minus 3 times 3 is 9, and I still have that x plus 2. Notice that I want to get rid of the parentheses in the numerator so I can start combining like terms, but it's not just the 9 that gets distributed, it's a negative 9. So that gives us 10x minus 9x minus 18 on the top. I never want to multiply out the denominator. I want to keep it as the LCD. Combining like terms in the numerator gives you an x minus 18 on the top, still all over that least common denominator. Since there are no more like terms on the top, it's just a matter of can we simplify this down any further? Because the numerator does not factor, I cannot simplify because there's nothing on the top that's the same as the bottom. So this would be my final answer. Here's a quick refresher of the identities that we've talked about in the past. So remember, we've had reciprocal identities, quotient identities, Pythagorean identities, and here we have these even-odd identities. So what we're going to do is we're going to review these concepts by evaluating without a calculator. So here's what I mean. Say we want to find the exact value, once again, with those identities, but no calculator involved. So notice this first one says the cosecant squared of 2 pi over 7 minus the cotangent squared of 2 pi over 7. The first thing I notice is that both of those terms are squared. Well, what identities deal with squared terms? The Pythagorean identities. And more specifically, in this case, 1 plus cotangent squared of x equals cosecant squared of x. Now, those x's can be replaced with any type of number as long as they're the same. Notice that 2 pi over 7 is essentially the same number, so we know that it's going to follow this rule. But they took that Pythagorean identity and they just manipulated it a little bit. Notice that if I subtract that cotangent squared of x over to the other side, now I have the subtraction problem that I am looking for. And notice that what it equals then, you're left with a 1 on the left. So because those angles are the same and I'm subtracting the cosecant squared minus the cotangent squared, our answer is 1. Looking at problem number 2, cotangent of pi over 7 minus cosine of pi over 7 divided by sine of pi over 7. The first thing I notice is that that second term is cosine divided by sine. That's one of our identities. That's the quotient identity. Notice that cosine divided by sine is really the same thing as cotangent. Once again, we can replace x with any of the angles as long as the angle measures are the same. So I'm going to keep that first cotangent of pi over 7 as it is, but I get to replace that second term with what it represents. It is really cotangent of pi over 7. Notice that we're subtracting the same thing. When you subtract the same thing, you're going to get 0, and that would be your answer. If we continue doing a few more, notice that the next one is the cosine of 33 degrees plus the cosine of negative 33 degrees. My second term has a negative angle. That's going to fall under this even-odd identity. If we look at the cosine, anytime we have a negative angle, it really is equivalent to cosine of the positive angle. So what I'm going to do is I'm going to keep the first cosine exactly how it is. I'm going to replace that second term with its equivalent, which is the cosine of 33 degrees. The negative angle gets to turn into a positive. So notice that now I have two terms. They are like terms. I get to combine them. If I'm adding one cosine plus another cosine, that's going to turn into 2 cosine of 33 degrees. This would be my final answer. In the last one, we have 4 times the sine of 24 degrees times the cosecant of 24 degrees. With the two trig functions that I see, sine and cosecant, there's a relationship there. If you look at your reciprocal identities, they are connected. Cosecant is the same thing as 1 over sine, or sine is the same thing as 1 over cosecant. So you could use either one of those, but we have reciprocals. I'm going to keep the 4. I'm going to keep the sine of 24 degrees, but now I'm going to replace cosecant of 24 with 1 over the sine of 24 degrees. Because we have reciprocals, the sine of 24 degrees multiplied by 1 over the sine of 24, they are going to multiply into the number 1. So then now we have 4 times 1, and my answer is 4.